So today we're lucky to have Josh Engels visiting from way across the river at MIT.
Practically a different country.
Practically a different country, and even in a different type of department. He's in Max Tegmark's lab, and so Josh has been making a name for himself in the last year or so by taking a really interesting and skeptical look at sparse autoencoders. He had a I don't know if it was a blog post or a preprint that had a very interesting title that said, sparse autoencoders, are actually good for something. And then there was a title change that got some attention, where he became more skeptical of them.
Yeah.
And so it looks like you're going to talk about that
Yes.
that adventure a bit. Is that right, Josh?
I will talk about it a little bit towards the end.
Okay.
I'll talk. Yeah, I'll basically kind of give a tour of some of my work on Sparse Autoencoders. Talk a lot about the multidimensional features work, which I still think is quite cool.
Oh, that's very cool.
And then also talk a little bit about the work we did, like studying the dark matter of Sparse Autoencoders, like what they're missing, and then also about this probing work.
Okay, excellent. Yeah. So looking forward to all of it. Yeah. Welcome, Josh.
Right. So yeah, I think this talk is actually pretty timely now, because I don't know how you've been following the Twitter sphere recently, but there's been a lot of interest about SAEs on Twitter in the last week, kind of from both directions. DeepMind recently put out a new post saying that they were probably going to stop working on Sparse Autoencoders, and then Anthropic put out like a really big post from the whole interp team that looked at like a bunch of really interesting case studies. And so I think there's some kind of like cognitive dissonance and cross wires right now in the community of just how useful are sparse autoencoders and then what's going on with the technology. So I'm going to give kind of an intro that talks about sparse autoencoders, talks about some of my work on them, and maybe I'll speculate about where I think the field should go. Yeah. Okay. Yeah. Talk about the background of SAEs and then some talk about some limitations that my work has found. Maybe some progress, and then some closing thoughts. Okay, so also just want to say, like, feel free to interrupt or like ask questions. It can be dynamic. So yeah, I guess in this talk, I'm mostly focusing on the representations that models use. I think this is maybe not the only thing you need to understand models. Like, you might also need to understand the computations that models do, but understanding the representation seems like a really good starting point. And one nice thing I think to point out is that there's this Platonic representation hypothesis, which is that this did not come from us, it comes from Hu et al. This is Philip Isola's group at MIT, which is this hypothesis that as models get bigger, the representations that they learn kind of converge for like a bunch of different reasons. Maybe because in order to predict many things well, it helps to have like a small set of the same representations of like the true world, or maybe a bunch of other kind of learning theoretic reasons. But just empirically, it seems like this is like human perception, and these are other models, and this is like color. And basically, in color, it seems like all these models are kind of learning similar maps of color. And then this is kind of true of a bunch of representations, and kind of the reason this is nice is because we probably need to study a couple models, might be able to draw conclusions about the representations of a lot of models. So yeah, in this work, we're just going to study a couple models. So okay, quick refresher. You guys probably all know this, but I'll just be getting some terminology. How the transformers work. Basically, you have a bunch of tokens. Those go to embedding vectors, and then you repeatedly do two things over and over. You like mix them together with attention, and then you do processing on top of them. That's the MLP, and then you just repeat that. And then I'm going to call these vectors like that are between the attention and the MLP that are getting added to like the residual stream, which is kind of like a McInterpy way of describing like the model's hidden states. And the residual stream is really nice because it's the only way to communicate between layers. So if you study just all the residual stream in a certain layer, it's like a nice bottleneck. It has all the representations the model's thinking about. Right. So now that we have this bottleneck, that kind of is all like we have this, we can look here and say everything the model is thinking about that it uses to predict the next token is stored in the residual stream. the natural question to ask is how representations are actually stored in the residual stream. What does the information in the residual stream look like? Is it just a bunch of random noise, or is there kind of like more structure there? And so the really simple explanation that would be really nice would be if each dimension in the residual stream store a single concept. So you have, a 10,000 dimensional residual stream. You have one dimension for, cats, and one dimension for dogs, and one dimension for cars. If this is, like, say it's an image model. Unfortunately, as like this awesome paper from Chris Ola in 2020, I think this is like zooming in, studying circuits. But this is like in the inception V1 model. It's usually not the case that neurons are monosemantic. Usually each neuron represents many things. And in fact, this is kind of necessary because if you think about it, a language model knows way more than 5,000 or 10,000 concepts or whatever the dimension of the visual stream is. And so it's not really plausible to just have one neuron for each concept. Maybe you could imagine training a super, super wide sparse model, but as of now, those are not what our models look like. I think that's a pretty interesting direction, though. Okay, so how are one hypothesis to how these representations are stored in the visual stream is the linear representation hypothesis, which is that basically most concepts in the model are stored as one-dimensional vectors, and they're all kind of stored almost orthogonally. And if the model wants to, and as long as the model wants to represent like only a sparse number of these, then it can kind of just store the sum of all these vectors as the activation vector, and then it can actually decode these vectors like relatively losslessly. This is like basically like some like really classical like sparse coding literature, where if you have an overcomplete basis, but only a sparse amount of the basis is active, then you can actually basically decompose. You can decode which things were active. Yeah, so this is just an example. If you have the sentence, the orange cat jumped, then maybe the model has one feature for orange, one for feline, one for action, and the representation is just the sum of those things. And this is also a hypothesis of like why linear probing works so well. Because if you have, say you're trying to probe out orange, right? Then you can have a probing direction that's like very similar to orange. Maybe it won't be exactly orange because you want to also be orthogonal to as many other concepts as possible, but it's kind of most in the direction of orange. And then whenever orange fires, the probe will fire. So now we have this model of the activation space. How do we actually, get all of these concepts? How can we get like a listing, an enumeration of all the concepts and models thinking about? And this key idea that I guess is in the title of the talk is sparse autoencoders. So the idea is that we can train a basically one hidden layer MLP to basically have a super wide and sparse hidden layer. So you have a super wide hidden layer, then you project back down and try to reconstruct the input. But you additionally require that this hidden layer, there's only a sparse number of the neurons that are actually active. And the hope is that like, you have one neuron here that's activating on feline and one neuron here that's activating on orange. And the idea is that hopefully the best minimum loss solution for this model, for this network, is to learn actually learn one neuron per concept. And you just train it on like a bunch of hidden activations from the model. And in practice, we do find that these hidden neurons are a lot more monosemantic than the original neurons of the activations. And yeah, I guess this is just this is from like I think scaling monosemanticity, or maybe the original dictionary learning anthropic work, where they basically find like a bunch of different, some pretty monosemantic features that they label. But there's some limitations here. I guess before I talk about limitations and lead into the work, any questions so far about the background? I don't know. Probably it's review for lots of you guys.
Just
Yeah.
like I think I understand the general premise, but like how good at reconstructing the hidden state are these models? It seems like that's
Like the SAEs.
right.
Pretty good. I would say usually you can get, depending on the model and how wide and how much you're willing to allow sources, but I would say usually greater than 90 or 95% of the variance you can explain. Depends on the model. I think bigger models, it's harder to explain as much. Another thing you can look at is when you insert the reconstruction back into the model, how much of the loss do you, or how much, what's the cross entropy loss difference downstream?
Yeah.
And typically for like reasonable SAEs, it's something like, I think Leo Gao, and they did train on GPT-4, and they found that it's like equivalent to a model that had been trained with like 10% of the training compute. Even though, so the cross entropy lift difference is like pretty small, but because like small cross entropy loss differences are like pretty big training. So it's like maybe if your model has like cross entropy of like 1.6, it'll now have a cross entropy loss of like 1.7 or something on like some like pile distribution or something. But like that actually turns out to be a pretty big difference in terms of like effective training compute.
So missing out on 90% of training seems like a big deal.
Yeah.
Like, so maybe
Probably.
they're not that good.
Well, it depends. Maybe they're still capturing like a lot of the representations. It's yeah, it's not really clear. Like what is it missing, right? Like is it missing things that we don't care too much about, or is it kind of missing like the actual things that make GPT-4 different from GPT-3?
Gotcha.
Yeah.
So and we don't really have a nice way of
Yeah.
measuring that yet.
Yeah.
I guess
Yeah.
have you like played with a model that's just like full SAEs and subjectively just
Like you're saying replace every layer with an SAE?
yeah.
Or even just one layer.
Or just one layer. Yeah, I think it feels similar. Yeah, I don't know. I guess I haven't really played with it too much. One thing you can do also is like say you want to steer a model. Like one thing, like for example, Goodfire has done is like trained SAEs on models and then used the SAE vectors for steering. So then you don't even need to insert the SAE reconstruction in. And it's like SAEs might be useful even if they don't perfectly reconstruct the output.
Oh yeah. It's just sort of an interesting question.
Yeah.
Like you had a paper you're going to talk about dark matter.
Yeah, yeah.
So maybe that's relevant.
Yeah, definitely. Like yeah, maybe like you were saying, there's like these pointers. Like maybe the reason that you get worse loss because you're just missing all the pointers or something, right?
Right.
Yeah. Yeah.
Oh, another technical question.
Yeah.
Because without that much experience in training SAEs, so what's the level of sparsity that we typically get? Like, so if you put an ordinary representation vector through,
Yeah.
then how much sparsity is the SAE like typically achieving?
You can kind of choose what you want. There's like a trade-off between sparsity and reconstruction. I think pretty normal is to have like an L0, which is the number of non-zero hidden neurons, of around like 50 to 150 or so.
Okay.
Yeah.
In like a thousand dimensional.
Yeah,
Yeah,
I mentioned
how big is the SAE? Usually like
50 to 150 out of
maybe like order of like 20,000 to a few 100,000. Yeah. So usually the blow up factor from the activation dimension is probably only order of like 8 or 16 or something, or maybe even bigger, 32. But then usually you have like 10 or 20 or more times fewer active concepts. So there's some limitations of the linear representation hypothesis, LRH for short, if you're in the know. I guess one thing is that, so if you look at this plot here, right, like this is like a UMAP of all the features, and they're clearly like not randomly almost orthogonal. Like semantically similar feature vectors that the SAE finds are actually like closer together in the activation space. And can we say anything more than almost orthogonal, or even say anything more than that, like similar vectors are close together? And are really, I guess, a kind of a question off that David and you guys touched on this, like, what's the correct mediator? Is that are one-dimensional vectors even the correct model of like what an atomic feature is? And if not, like what types of features might be inherently multidimensional, and how might we find them? What would they look like? So here's the LRH, activation of sparse linear combinations of meaningful feature vectors. And what we hypothesize is the multi-D representation hypothesis, activation of sparse linear combinations of meaningful feature manifolds, aka multi-D features. So this paper, what's called non-linear features are one-dimensionally linear. Used to be called non-linear features are linear, but we added the one-dimensionally linear because I think that more clearly articulates the aspect of linearity that this paper is kind of finding evidence against. But yeah, so basically we find in this paper, we kind of argue that many features might be inherently multidimensional. It doesn't make sense to think of them these kind of like one-dimensional sparse autoencoder latents. And so here are some examples we find. I'll talk more about this in the next few slides. But we just find like for days of the week and months of the year are kind of the clearest examples where these kind of representations lie along a circle. Okay, so what do I mean by a multi-D feature? Like what does this even mean? So we kind of define a feature as a function that maps some subset of like the input distribution, the tokens, to a k-dimensional point cloud. And we say this point cloud is reducible if it is basically composed of two lower dimensional features. So if there's just two independent features that make up this blob, then we say it's probably not like a real multi-D feature. Or if it's composed of two features that basically never occur together, because lots of times you might have things like, submarine and like, Mars that are like basically never occur in the same sentence. And so they're like kind of anti-correlated, but we don't want to say that this is like some multi-D feature. There has to be some more interesting relationship between these concepts. It's like I don't know if this is a perfect definition, but it's kind of like a kind of a first pass statistical test that you might run. And then a circle, for example, is neither of these things. There's no way to decompose this into two, kind of like to project this onto a basis such that the basis is independent or that the basis like never co-occurs together. And so we can actually run these tests on a bunch of clusters. So why do we want to run this on a bunch of clusters of SAE features? So the idea is that there's some feature space in the model, and if there are truly some feature manifolds kind of in this space, then we might expect many SAE features to be learned that lie along these feature manifolds. Like say there's some circle, you might expect a bunch of features to kind of get learned that lie like spokes along a wheel for that manifold. Basically, any places that there are there's density in this feature space, we might expect there to be many SAE features that are learned. Except sometimes when there's density, we might expect this is some more interesting concept. Sometimes it'll just be density because there's like a lot of features there, but sometimes it might be more interesting. So what we can do is that we can cluster the SAE features, kind of finding these areas of density in the feature space. And then for each of these clusters, we can run these statistical tests from the last slide to kind of figure out, is this like a real multi-D feature or is this just like an area of density? And when we do this, we find that like some of the features that are most irreducible by these definitions, kind of like with these nice multi-D features just kind of pop out. And so that's really cool. It's kind of like an unsupervised way to maybe find multidimensional structure in models.
What's the distance metric for clustering?
We use a couple, I think mostly cosine similarity between the decoder vectors. Yeah, and then the clustering, we tried a couple of clustering techniques in the paper. But yeah, I think it's not totally clear what would be the best way to do it. Yeah, and also I think that there's some argument that maybe clustering wouldn't have worked to find all types of multi-D features, because it kind of assumes that you kind of learn this a bunch of SAE features that lie along this multi-D feature, but maybe that doesn't always happen.
Have you also seen this line of works about feature absorption and feature splitting?
Yeah.
So when you are clustering these concepts, do you also find that they can be like coalesced together to a single concept sometimes?
Yeah, I think so. I think totally you get that. Yeah. In fact, in the days of the week thing, in the months of the year, we actually see some feature splitting. I forget if you can, it's on here, but like there's also like direction for like, I think it's on a different model, the Mistral model, but there's like a direction for like spring and fall and winter and weekend or something. And so you might imagine those are kind of like splitting off from like days of the week or the months directions. Or maybe those are just atomic concepts. Yeah, I don't think we look too much at clusters of like non multi-D features. Like we don't look at them too much, but probably other people might have looked at this.
So why I was asking this question, because now the difference between actual multi-D concepts and some kind of like an atomic concept that got splitted, the difference between them becomes a little bit shady.
Yeah,
right?
Definitely. I think, like the difference we argue is that, well, one thing is you can just look at them, right? And you're like, oh, like this is can mostly be represented as like a 1D feature or something. And that's what we kind of try to formalize with these statistical tests.
Okay.
But I agree, it's not totally clear. It's a little bit also, we're also appealing a little bit to like human intuition, maybe,
Okay.
right? Like at the end of the day, we're kind of saying like we're like trying to find areas of dense structure in these features, and some of them like really pop out as like this interesting multidimensional structure, and like this is pretty clearly not just like a one, you can't just reduce, it's like this is important structure. And then we try to like formalize it a little bit, but you might not really need the formalization.
Awesome. Thanks.
So is the idea you can only, you need two parameters to parameterize a circle?
Yeah.
And so it's not one dimensional, I guess, is that?
Yeah. And also, I guess another way to think is just like the relationship between these features is like very structured. And it's not just like random almost orthogonal stuff.
So like, did you look at these other ones that are more in the corner?
Let me see. Do I have it here? Yeah. So here's some like bonus like what other features does it find? It finds a lot of like common tokens and letters, which might be this feature splitting thing. So like here like is n, and like this is the n token, and we kind of split it out by like capital N, N with a space, another capital N, and like, yeah, this maybe is some interest. Like there's this really cool set of work from Adam Shai and Paul Reachers about and some other people about belief states in language models, which is like, assuming that the model is like, assuming models are like trying to predict like next tokens in like a hidden Markov model, like they might have like really interesting like fractal structures, and like maybe these like common tokens are like also similar of like where the model is like has this like kind of dense fractal structure for like when it's doing something that's very like a common token or something, but I'm not really sure exactly what's going on in these examples, but they're interesting to look at.
Oh, can I ask a very preliminary question?
Yeah.
Having never worked in SAEs.
Yeah.
What is the why are we trying to find only linear SAEs? Why not nonlinear? Why not two-layer SAE?
You could do that, like a two-layer encoder or two-layer decoder or something, or two-layer encoder especially.
Like with nonlinearity in between, like why is the linearity so desirable here?
Right. So one thing you totally could do, I think, that doesn't hurt interpretability that much, and people have shown this, is to use a more powerful encoder. So the idea is you're trying to come up with a bunch of latents that reconstruct the space. It doesn't really matter how you get them, as long as, but I think if you make a nonlinear decoder, it's a little less clear how your latents relate to the actual model activations that you're trying to reconstruct, because now you have a bunch of latents, but they're being like combined before they reconstruct the activation. So I think a linear decoder is like probably what you want. You could have a more powerful encoder. Does that answer your question?
Right. So if I were to have a dual layer encoder with nonlinearities,
that's fine, I think.
Then it wouldn't, like, this wouldn't show up in the first place.
I think it would. I think it still probably
still
would. I suspect it still would. Because if the decoder is still linear, you have to reconstruct the circle somehow in the decoder. And so
right. So you're saying linearity in decoder is preferable because you want to interpret it.
Yeah.
Like how are these being?
Exactly. Yeah.
Can we not interpret nonlinearities? Like if you have a simple ReLU or something.
Then you have to say like, okay, you have these features that are active in the hidden states, but now they're being like combined in like this dense way. Like, so now it's like a lot harder to figure out. Because the nice thing about having a linear decoder is you have your latents, and the reconstruction is just a sum of the latents, a weighted sum of the latents, right? Like each activation times the decoder. And now we have these combined things that are combining them, and it's a lot less clear like what the activation actually is.
So these, so like qualitatively, let's take a look at these clusters that you found under. Right. So you describe the cluster as such, and another cluster as
N, the letter N.
N, and so, but you've got it's multidimensional. So like, what is it using the other dimensions for? Like, so for your previous paper, right? It was pretty clear that you use the other dimension for the days of the week.
Yeah.
Which day is it? So is this using the other dimension to figure out what kind of N it is or something, or what? Like that's what I'm trying to understand.
Yeah, I think yes. I think exactly. I think it's using. I mean, it's a little hard. Maybe PCA is not the right way to look at this. But yeah, so like it's colored by the different type of n, and
what are the different types in the?
there's like a lowercase n, a capital N, an N with a space, capital N with a space, and then a few other like n weird n tokens, maybe just a space token. Yeah.
And what about the suches?
Such as we have a lowercase such, a capital such, and then those are the biggest ones. And there's also these, a, as, such, so, including. This is like the top 10 tokens.
Oh, like similar words that that play the role of such.
Yes. But yeah, I don't exactly know. It does seem like there's some interesting structure here. I'm not really sure exactly what it
okay. Yeah, that's what I wanted to know.
Yeah, okay, cool. Yeah, we have in the paper we have in the appendix, we have like the top 20 or so clusters. Okay, now another interesting question is, do models actually use these circles for anything? And so the task we look at is like this natural modular addition, where we have questions like, let's do some day of the week math, 2 days from Monday is blank. Let's do some calendar math, 4 months from January is blank. Interestingly, models actually can't do normal modular arithmetic. If you just like language models, I guess who was training? Yeah, you were training like on actual. You're just training a toy model to do modular arithmetic. It can probably do that in that case, but language models can't. But they can do this kind of natural stuff, which I think in and of itself is kind of interesting. Imperfect generalization. But so models can do this task, and we can do a PCA of the hidden states and find the circle in the months and the days of the week. But we can also intervene in the circle. We can, and not just along kind of the outside edge, we can also intervene in the center. And we get these really nice plots where this shows like if you take a task like 2 days from Monday is blank, but you change the representation on Monday to like anywhere in the circle, then it kind of is predictable and that like the output changes in the way you'd expect. And if you change to 3 days, then you can kind of this circle rotates a little bit. So basically it seems like the model probably is using this circle. Now caveat for you guys, you do a lot of like patching and stuff. In order to get this to like work well, we have to ablate the other dimensions in the PCA because there might be like some other pathways the model is using to compute this. And if you don't ablate those, it gets more confused. Okay, some recent follow-ups. So this is kind of why we changed the title. So Chris Ola came up with this cool blog post that basically kind of makes the LRH be 2 parts. One is that like features are inherently one-dimensional, and the other is that features magnitude correlates with intensity, and you can add them together. And so we only show evidence against part 1. Casordis et al. With Stanford NLP group show some evidence against part 2 by finding these kind of like onion-like features in this really cool paper. Our evidence is only against part 1. This part 2 is in a toy model, so maybe it doesn't actually happen in language models. So we'll see. And then, yeah, this is the belief state stuff I talked about. I think that's really cool. And these are kind of multidimensional features, although in toy model. And Liv Gorton, in this really neat result, finds like the curve detectors in vision models also form a circle. Okay. Yeah, so Logan, right? Like Logan hangs out here sometimes. And Max. Yeah, so this was kind of the next kind of piece of work that I worked on Sparse Autoencoders, also somewhat kind of investigating what does Sparse Autoencoders like not learn. And what we find is that we kind of like study the SAE error object as kind of a like a first class object to study. And what we find some interesting things. One is that like the norm of this error term is very linearly predictable from the input activations. And moreover, the actual vector itself is like kind of just a linear transformation of the activations many times. And to me, what this is kind of roughly saying is that there's possibly some subspaces in the input activations that the model just isn't learning. And this seems kind of problematic. And then one kind of neat thing is that like it seems that the amount of linear error in many cases decreases at the same kind of rate that the reconstruction error goes down. And so it kind of seems like this nonlinear error component is kind of like we can kind of like project out the features we're gonna learn, and if I say like as the SAE is really wide, there's probably gonna be some chunk of linear error still left and some chunk of nonlinear error.
So how do you decompose these three components of error?
Right. Okay. So the linear error is just the fraction of the error vector that we can predict with a linear transformation of the inputs, and the nonlinear error is like whatever we can't. Yeah.
Fraction of the error vector that you can predict
with a linear transformation of the model activations. Yeah. So if like you had just learned like some random subspace of the input, then you could predict 100% of you predict whatever the orthogonal subspace was as a linear transformation of the input. Yeah. Whereas if you had just kind of learned like some random set, then I think it would be a lot harder to predict anything of the reconstruction of the error.
Does it make sense to you guys? So like the words you're saying, you know, they seem reasonable. It's just I haven't been thinking about this.
Yeah.
Yes.
Yeah, I think it is a little plausibly a little confusing. Like exactly what I think we're just trying to get a handle on like what is the error vector made out of? Is it mostly kind of like unlearned features, or is it maybe something weird the SAE is doing, or is there some like consistent
right. So does linear error correspond to it's just unlearned features, or which one is that correspond to?
I think linear error is mostly unlearned features.
I see. So like linear error is like, oh, if you sort of had infinite dimensional SAE, then you would recover all the rest of the linear error. Is that?
I think you wouldn't necessarily. That's what this is kind of showing, that there might even be linear error at infinity, which maybe is saying that some of these like maybe some of these features are like not linear. Like if linear error could be maybe modeled as like some like dense random noise that's really hard for a sparse representation to learn. Maybe impossible unless you have like an exponential number of directions or something. Yeah.
Yeah, that's what I'm trying to understand. So like why? So like
yeah.
Absent features. That's your curve of.
That's the curve of just like
increasing the size.
Yeah, that's just like variance explained as you increase the size.
I see.
Yeah,
I see. So what the heck is linear error? So it's just the error that can be predicted.
Yeah, from the activations.
So what do you mean by can be predicted? Like what's an error prediction?
Just a linear transformation of the
to go to a scalar or to go to a vector.
To go to a vector.
So you're right. So it's just a simple linear model of the residual.
It's kind of trying to say like, are there subspaces of the residual that the SAE is not learning?
And so your hypothesis is these are the things that are not one-dimensional, or these are the things that are not sparse.
Exactly. Yeah. Maybe they're not important. They're not important. So some things that are they're not like sparse or one-dimensional in the right way. Yeah.
They're inherently dense.
Yeah. And also the SAEs could learn dense things as long as they're low dimensional. But if you have some high dimensional dense subspace, you know, like say you just I mean, one thing is this could be some random Gaussian noise. Like say you just have some literal random Gaussian noise that you just add to your activations.
Right.
Then you'll be able to predict that. It's not totally clear that maybe, but I kind of obviously there's no noise in a language in a transformer. So.
But it might need it, right? It might be, I need
right.
I need to make some stochastic decisions. I have my own internal pseudo random number generator.
Oh, maybe
to allow me to do this.
Could be.
Right.
Yeah. Anyways, I should keep moving so I don't. Yeah.
Thanks.
So another couple interesting points that we find in this paper is that SAE errors can be pretty consistent across scales. So this is like per token error. And you can kind of see that you can predict a lot of how good you'll do on a much bigger SAE by how much you do on how well you do on smaller SAE. This is kind of more. This is like error norms, I think, but this is kind of more evidence that like some tokens or some things on some tokens might just be like fundamentally hard for SAEs to predict. And then just a little. This is just a little more analysis, kind of breaking down this like linear and nonlinear component, and finding that they're kind of fundamentally different in a few different ways. This is a few examples that you train an SAE on the linear error component, you do better in terms of like how interpretable the resulting features are, and also like the loss of the SAE is lower. Also, you can predict the norm better of the linear error than the nonlinear error, which we kind of argue in the paper. I won't get into too much here. Is like an evidence that there's more like unlearned features in it, as opposed to like weird stuff from the SAE. Yeah. Okay, any other questions here? And then I'll talk about are SAEs useful, which is the recent stuff on Twitter.
I'm sorry, can you
Yes.
recap the takeaways from this work?
Okay, sure. I think the takeaways from this work are SAEs seem to be consistently missing some subspaces of features. As they get bigger, like their errors are like seem to be correlated across scales. And it's like seems tractable to study SAE error. And maybe we can find some interesting stuff about like the non one-dimensional features in language models by studying what SAEs make mistakes on.
Can you actually find that subspace? Like in the language models, like what that subspace is that SAEs are missing? Then probably we should, if we are only interested in like understanding linear features, maybe we should take the other subspace and don't really bother ourselves with that subspace at all.
You could try doing that. Yeah, I mean, but I feel like that subspace has interesting stuff in it. Yeah, I'm not totally. I think it would be interesting to try to look. Also, it's not totally clear. So like this subspace that's linearly predictable also includes features you haven't learned yet, probably. So you don't just want to throw away the whole thing. There's like seems to be some part of it like at the asymptote, yeah, you could throw away the linear subspace, but like until you get there, it feels like you can't quite just throw it away because there's also like unlearned things that like as you make your SAE bigger, you want to get. Like there are like it's a combination of like true 1D features you haven't learned yet, and also maybe like some like nonlinear stuff you haven't learned yet. Some noise or something.
Also, I had a question about this figure.
This one?
The one in the bottom.
Yeah.
So to draw this figure, you had to boil your vector down to a single number.
The norm of so this is the fraction of variance unexplained. Okay. And so this is like if you just do the SAE, and then you can ask the asymptote, and then you can do that's this line, this bottom line, the asymptote of the top line. And this line is if you take the fraction of variance unexplained, if you have your SAE, and then you also do a linear prediction of the error, and you add those two, and then you look at the fraction of variance unexplained.
Okay.
Yeah.
Okay. Awesome.
This was alluded to by David at the start of the talk. We have this paper, Are SAEs Useful? A Case Study in Sparse Probing. This was Subhash, Sen, Max, and Neil. And yeah, this like you're very perceptive that we had this blog post at first that said something like SAEs, what are they good for? Absolutely something, which is a play on the old song like war, what is it good for? Absolutely nothing. And then we kind of had this update where we had a preprint where we spent a couple more months on it. We looked kind of more, tried to make the baselines more rigorous, kind of looked at more case studies. And we found that there really weren't that many positive results for SAEs in the end. So it was kind of a negative update for me on SAEs overall. And also for DeepMind, because Neil's on this too. Neil's the head of the DeepMind interp team, and they also had some internal results that were negative on SAEs. So yeah, I'll talk a little bit about sparse probing now. First, why do we expect SAEs to be good at probing? I think this is an important question because if we don't expect them to be good at probing, then the negative results of our paper are a lot less interesting. One reason is that other people have found positive results with SAE probing. So there at least should be some prior that like this is a reasonable thing to try because other people found some preliminary positive results. So Trent and Bricken from Anthropic has this cool blog post where they find that if you pool SAE activations together across a context, sometimes you win out on probing. Oh, by the way, sure, everyone knows linear probing, but just I'll recap. It's where you have a data set of prompts and targets, and you train a linear logistic regression probe on hidden states of the model to try to predict the targets. Right. I said that here too. Nice. There's lots of nice applications in AI safety. Detect deception, detect models being honest, models like self-aware of the benchmark. And okay, but so maybe there's some positive results here, some other maybe positive, like mildly positive results in literature. But intuitively, I think the argument for why SAEs might be useful is that they have this really strong kind of inductive bias for interpretability. SAEs are basically built to learn a bunch of one-dimensional vectors that are good for reconstructing model activations. And probing, like logistic regression, is also trying to find one-dimensional vectors. So you would think that in cases where it's pretty hard for probing to find a good one-dimensional vector, then kind of relying on this inductive bias in the SAE that's already found a bunch of like 1D vectors that you think are like pretty good, you should be able to kind of like use that as a nice inductive bias crutch to kind of do probing better. That's the intuition. So we look at, well, my shirt is inside out.
It's intentional.
It's a new style. It's a new style. So kind of following this intuition of evaluating on difficult tasks of probing where normal probing has a hard time, right? We look at like some pretty difficult probing tasks. So this is this condition, this thing on the left here is standard conditions. And so it's just normal probing of a lot of data. And we look at like 113 data sets, and this is like the average test AUC. And then on the right here, we look at some other settings. So we look at data scarcity, class imbalance, what is noise in the labels, and when the test set is out of distribution. And you can see here that all these settings, like indeed, the average performance goes down. So like these settings are harder for linear probes. Unfortunately, we also find that they're harder for SAE probes. And basically across the board, like SAE probes do no better than baseline probes. And there's this quick thing here about interpretability. Like maybe you might argue that SAEs probes are really just good because we can look at the latents that get identified by the probe. And we indeed find this does help, but we also find that that baseline methods can surprisingly also help in this setting as well, like in an interpretability setting. Yeah.
So by SAE probe, you just mean you take a latent and
I can explain here. Yeah. So yeah, what do I mean by an SAE probe? Great question. Basically, you take your class 0 activation vectors and your class 1 activation vectors. You pass them through your SAE. That gives you for each vector, you now have like a latent representation. And then you choose K of these latents, like where K is pretty small. The intuition is that like you want some like sparse set of SAE latents to make your probe. Here we choose them by the average difference between the class labels on each latent, but you can imagine other ways of choosing them. And then you train a logistic regression probe just kind of on these like lower dimensional latent vectors. And another question, I guess, kind of is that this quiver arrows I have here is, you might hope that, okay, well, SAEs might help on all data sets, but maybe they at least help on some data sets, right? Like maybe the reason this is lower is because it does twice as well sometimes, but half as well other times. And so we actually test this by taking like a bunch of different methods, both with and without SAE probes, and choosing the best method based on the validation AUC, and then reporting the test AUC to that method. And we basically find that this doesn't really, that the SAEs do not have a consistent advantage, even using this technique. So like this is not enough to like recommend SAE probes as like a tool in a practitioner's kit. Quiver in their arrow. Yeah.
Oh, so the way you choose the latents is you pass a bunch of 0 class and 1 class and you see what is the major difference. And those are the top K you choose. So intuitively you're saying if you club a bunch of these sparse latents, you could probably form concept representations for the class you're trying to, for the classification task. Right, like the top K latents.
Yeah.
If you club them together, they are the concept representations for the classification task.
Yeah.
Only then would it work.
What I
mean, only then would the probe give you like a very good accuracy. If these K representations work really well together to give you the classification. And you found it didn't work. So what if you use all of them?
You can. So we have I don't think I have it here, but we look at like K, which is how many you use versus the AUC. And 120 we in the paper, like for these plots, we use 16 to 128. And we basically find that beyond 128 doesn't help too much. So what it kind of like flattens out at some point.
Right.
Past like the first 128, 250, which is not so surprising. Like if you took a PCA of the activations, it would probably also be 128, 256, beyond which it didn't help that much to look at more dimensions. Yeah, so basically, like it doesn't seem to help too much to use more latents.
So that's surprising. So out of 10K, you have 128 is the maximum that you can club together for you to represent a concept good.
Yeah.
But then if you don't pass it through an encoder and you just use the latents itself, it's probably much higher.
Not much higher. Like it is a little higher. Like here, it's but it's higher. Yeah, it's higher.
So,
Okay, it's not much.
in SAEs here, is this like sort of the 128 case
Uh,
SAEs, or is the 16 case?
I think it's I'm not sure. I think it's probably the 128. But yeah.
Oh, okay. So earlier I thought you were saying that compared to other methods, it didn't work as well. So I thought you meant like compared to the latents itself.
No, it does worse than just probing on the original activations because you lose some information within the SAE, I think.
Right.
Yeah. Yeah. I actually don't know. It's a good question, David, if this is 128 or 16. We should check that. But we add both 16 and 120 to the quiver. So if 128 really help, then it should do better. Another thing we find is that the multi-token results from Anthropic didn't use like a great baseline. They were exploratory, so it's not. I don't think it's like totally their fault. But if you use like an attention probe baseline instead of just like max pooling over the original stream as a baseline, then even though multi-token probing helps, it helps a lot less than it would otherwise. So I think it's kind of a lesson that like if you're gonna spend a lot of time optimizing your new technique, you should spend a lot of time optimizing baselines as well. And then the interesting thing here is probe interpretability. So certainly we find that SAEs can help with interpretability. Like SAEs can identify spurious correlations. You can look at the top latents that activate that are like in a probe, and you say, oh, like this is a punctuation feature, which is what we find in one case. This is like a spurious correlation because you can see like, oh, most of the positive class end in question marks while the negative class end in spaces. So SAEs can help you identify spurious correlations in this way. But it also turns out that baseline methods can identify this sort of spurious correlation. If you just look at like on the pile, the tokens that are most similar to your baseline classifier, it turns out they're also punctuation. And so this is like, it turns out, I guess what this says is that like maybe like interpretability is in some ways like easier if you're just a little creative. You don't need to use like high-powered SAE tools. You can just like take your linear regression probe and dot it against the pile. Okay, that's the end of the probing discussion. Any questions there?
So let's say you had an SAE that actually was good at reconstructing the hidden state. Do you think you'd find better latents for probing? Like, I guess, yeah, like I feel like 90% of the training loss
Is a lot.
is a lot.
Yeah. Although I think that many of the concepts are that the probes look for are maybe not in that 90%. I don't know. They're like nouns, which I feel like SAs are pretty good at getting.
I see.
But maybe. Yeah, I think my hunch is that a lot of the problems that make SAE probing not work as well are not the fact that it's not representing things, but the fact that all the other problems that I see is like feature absorption, where concepts go together, or feature splitting, or feature hedging, which is this new thing from David Shannon, where features like kind of move towards things that aren't in the SAE. So there's kind of all these problems with SAE latents, and I think that's one of the I think the kind of the takeaway is that I don't think SAs are finding like true concepts. I was excited at first they were a long time ago, but now I just think that maybe there's just some way of characterizing like the model's like feature manifold. And if you don't have like some like true characterization as manifold, there's kind of not much of a reason to expect that like this characterization will like help you do better probing. I think that's kind of my intuition nowadays, if they're not like true model concepts.
It's sort of a tiling of the manifold.
Exactly. Yeah. Yeah, and so they're not like super crisp atomic concepts. They're just like some imperfect tiling. And at that point, the inductive bias doesn't really seem to just help over logistic regression, like L2 inductive bias, like L2 regularization, which is just like really good, it turns out. Like linear probes are just like really good.
Yeah, but
Yeah.
you need data, right? So that's the maybe the
You
thing
need
that
data.
seems
Yeah,
nice.
so this is unsupervised. That's true. But in many cases you would have data. I guess, yeah, I think SAEs in terms of like an unsupervised discovery method for like learning things about your model, like that they can do. It's hard to make a benchmark for that to see if they're actually helping over something else. Like, I don't know, asking the model about like what it's thinking about or like guessing things and checking them. But I do think that's the most promising avenue for SAEs. One kind of last thing I'll talk about is a recent like kind of more interesting methods paper like that we found to maybe improve SAEs a little bit. It turns out that if you take a frozen SAE, but then fine tune the rest of the model to have low KL with the model output, you can actually get like a pretty big jump in performance. Like you can recover like up to 60% of loss gap to no SAE. So I don't know if this will solve any of the problems that we talked about before, but I just think it does solve the kind of this problem of like inserting the SAE, you know, is like 10% of training compute. Now maybe it's like 20 or 30%.
Oh, so I missed it. So
Yeah.
this is just using a different loss.
So what this is you have your trained SAE, and then you just fine tune kind of using LoRa the model, the rest of the model around the SAE
Oh, to adapt
to adapt it to have low KL. So like I think it's kind of clever because you're like changing the model instead of just changing the SAE. One of their reviews didn't like that very much. He was like, make interpose to interpret the original model. But I think it's kind of cool to say like, well, what if we relax that? What if we just want to have a combined SAE model system that's more interpretable?
So you might have this analysis, right? I'm interested. Do you think the low rank adapters are learning how to make the model dumber or how to cover the gap that SAE did cover?
Yeah, have you done any like evals on the like mixed models?
Yeah.
Like how much worse they get, or if they
Yeah.
get
So
worse?
do we have it here? Like, I don't think I have it here. We test on like the classic evals. Like we test on like MMLU and a couple other things, and like it does get smarter. Like than the model, just the SAE. I think it's mostly fixing the like places the SAE messes up. Actually, there was a recent work from Adam Carbonin that finds you can get a lot of the benefit here by just like taking a trained SAE and then just fine tuning the SAE on KL. So I don't know how much, like a lot of this might just be like fixing things in the SAE, I guess, my intuition. Yeah. I do think overall, I know Adam, so Adam found that you can maybe a lot of the benefit here without training the rest of the model. I'm just kind of still excited about methods that like take the model and like try to improve it to make it more interpretable. Yeah. Yeah, helps other metrics. I guess okay, I'm gonna end with some speculation. I think what is the future hold for SAEs? I wrote this actually before the recent stuff from Twitter, so maybe I'll just kind of go off book a little bit too. But I think one kind of important question is are SAEs like useful for real downstream tasks? Like this recent SAE work from Anthropic, from Sam Marks, like using it for auditing. They find you can do it without SAEs, but maybe SAEs will help you do it faster. And then I guess I'm also interested in like what auxiliary losses can we add to get like better latency in some way? Like if this is just some like tiling, as David said, of the SAE's feature space. How can we get like better tilings, like more interpretable tilings? Because I think I've kind of given up on like the fact that SAEs are like discovering like true atomic features. Maybe we can say, okay, like what's an actual useful set of features? Like what gives us a lot of control or what gives us a lot of understanding? I think adding that to the SAE loss function somehow would be really useful. And then I guess one question that also is kind of brought up from the Anthropic work is maybe like transcoders or cross-layer approaches help in some way, or maybe like the Apollo, or maybe you just kind of need the Apollo parameter-based decomposition. Like maybe activation space is just kind of doomed. I guess I'm also just pretty excited now about like supervised techniques, like just like trying to make probing really good, or just like classic, David Bow style interp, like do patching or like just like look at the model and figure out what's going on instead of trying to like come up with tools that are general. But I don't know. Anyways, that's the talk.
Cool. Can you go back once?
Yeah.
Let's see. So have people really not tried just like adding the KL loss to SAE?
Oh, okay. They did try that. So we do compare against that. That's the red line here.
Okay.
It trains a lot slower, and people haven't been using it because it trains slower. We didn't try the like take your top KSE and just train on KL at the very end, which turned out to like work pretty well. Which is what Adam tried. I think it gets like most of the way to our thing.
Gotcha.
Yeah.
So here's a silly question.
Yeah.
So like SAE features seem to have like nice interpretable properties. Can you like take the data that they activate on as like to train probes, and do the probes that you train end up with the same latents, or are they better than the SAE features that you started with?
That's a great question. I don't know. I don't think anyone's tried that.
Of like, oh, like maybe this is a punctuation thing. So then you like have some data set where it's like, okay, punctuation versus not punctuation or something.
Oh, so you wouldn't use the actual, so like would you use like the label to like generate new data or
Yeah,
something?
maybe.
Yeah, I don't think anyone's tried that. Yeah, could be cool.
I also wonder if you, so say you train a linear probe on a base model on like a concept that you think is like definitely represented with just one feature in the SAE. Like you look at the SAE features and you're like this concept, that concept, that you train linear probes on the base model, and then you take all of the positive activations that you found in the base model and run them through the SAE, calculate the sparsity of that, and then compare that to the sparsity of like just random text that you run through, right? Has anyone done that? And is the sparsity like, is that ratio kind of high where there's like much more sparsity in these things that you think should be sparse compared to just like random stuff that you run through?
I don't think anyone's tried that. I kind of suspect that it would be similar because even in cases where like there's not really many cases where like one feature fires. Like certainly there's like times when like fewer feature fires, more feature fires, features fire. But yeah, maybe you could kind of identify like tokens or I'm sure like things like the beginning of sentence token, for example, like BOS token. That usually just has like, if you train it well, it just has like one feature. I mean, most people don't even train on it because it's just like a constant. But a lot of times I think there's like lots of kind of like subtle like other things hanging around in activations that are like hard to disentangle from like a single dominant concept.
I still like, on this theme, I still like Eric's old paper, his quantization paper, where he made this attempt to identify these monosemantic predictions, where if you look at his idea was if you look at enough text, then once in a while, there's like a word prediction that the model makes for one reason, right? Usually there's, usually word predictions like have lots and lots of different, reinforcing, redundant circuits or lines of logic that simultaneously let the model to predict that same word. But once in a while, there's just one dominant thing that it's doing. And so he like tries to distill those things out. I think it's kind of an interesting idea.
Yeah. I do think that methods that take like what Eric does is he clusters gradients.
Right.
I do think if you did something like did some sort of like sparse autoencoder gradients or maybe this attribution parameter decomposition stuff, then it's kind of, then you don't have to have it by itself. You can like kind of pull out the mechanism when there's other mechanisms going on at the same time.
A little fancier than clustering.
Yeah, a little fancier. Exactly. I think SAEs are basically fancy clustering, where things can belong to multiple clusters at the same time. That's what dictionary learning basically is.
So I like that you started the motivation with the polysemantic hypothesis, and then SAEs are probably a way to get these individual features. So can I assume that the SAE features that are popping out are the true features that the model is encoding, or is it probably some weird mixture of?
I think it's the latter. It's a weird mixture. Also, I'm not even sure what it means. I don't know what true features means anymore. Yeah, what's a true concept exactly? Yeah, I kind of this is the mediator paper, right? Like I think that I would probably best model it as like some sort of hierarchical thing where you can always break down kind of concepts more if you want, but but I don't know what it means for it to be like a true level. Like I think SAEs are finding like a tiling of the feature space, really like that wording, the tiling of the feature space, that works to reconstruct it. But I don't think there's any sense in which like they're the true level.
Right. So the reason I asked this, most of the SAE features that got popular, are the ones that we can interpret.
Yeah.
And there's this like there's this note always in the paper that says, oh, we found like 20,000 features, out of them 100 are like really cool. Here are these 100.
I think so there's a lot of auto-interp stuff research about like automatically interpreting latents and SAE latents and trying to figure out, and I think so many of them are interpretable, I think, in practice, not just like 100 out of 20,000.
60%.
Yeah, I would say that sounds about right. Maybe a little more, maybe 60-70%. But even the ones that are interpretable, it's like interpretable, like you're like, oh, this fires on periods, but like not all periods. And why doesn't it fire on all periods? Like I don't know, right? And so there's like a specificity and then like sensitivity part where that it's also hard to measure certain things, because if like a lot of metrics like detection, like you say like does the feature fire in this place, but it doesn't say like does it not fire in like some similar situation. So like how do you find hard negatives, right? How do you find like places where you like the explanation thinks it should fire but doesn't actually fire? So I think automated interp is like, I have it here as like, I think it would be good if we made it way better.
Right.
But yeah, because it's kind of not entirely clear how good the features are beyond the fact they're just like better than neurons.
Right. So that's my question, right? Like, so if you're saying not all features are good, or like some sense not so clean.
Yeah.
Right now, I say maybe there is. I'm not aware of it. We don't rank the features. Like, what is the feature that the model?
We don't rank them.
We don't rank them. So if you were to rank them, what's your hypothesis? Like, do you think it's the interpretable, like human interpretable features that will surface on the top, or these noise sort of features?
Rank them in sorry, what way?
In terms of like what the model
Like best for loss,
Yeah.
best for reducing loss.
That's for loss. DeepMind does something like this where they like do a weighted auto-interp score by frequency. I guess my intuition, well, one thing is that there is a bunch of high frequency features where they seem somewhat uninterpretable. Actually, work I didn't talk about here is that where we look into it, we find like maybe some of the high frequency uninterpretable features maybe are actually interpretable.
Right.
But yeah, it seems like so many of like very high frequency stuff, which is responsible for a lot of model loss, is uninterpretable. And then yeah, I don't know kind of what the rest of the distribution looks like too much. Yeah, I think
for the scoring things, and I'm not an SAE person, so
Yeah.
you can tell me if old people have been doing this, but I really like these causal tests. So like I really like what Chris did in his application of SAEs like last week, where he's like, oh, the way we can tell the difference between a good SAE feature and a bad one is that when we transplant it, it has clearly causal effects, and a lot of them don't, right? But then some of them do, and that's how you can tell the difference between a good one and a bad one. I feel like there's higher order causality. I think that for these representation vectors, I like in Lisa Hutt's paper about how they're like, hey, can you transfer this to a different model? Can you like distill this latent into another model and actually have it learn this behavior, which is kind of this meta hyper version of causality, which is kind of interesting. And so like I like these causal tests. I feel like a lot of the SAE work is right now very worried about reconstruction and about some correlative things.
Yeah.
And I feel like it's not necessarily, it doesn't smell to me like the most reliable compass.
I would agree. Yeah.
Right.
There is some like SAE bench has some stuff on downstream effects.
Yeah.
Like steer. I don't know if they have a steering one, but they should.
Right.
Um,
John isn't here right now, right? So that's
Yeah.
Yeah, cool.
yeah. Yeah. I agree. I think evals is a big problem with SAEs.
Right. Like, when the SAE community is onto something good, would they know it or not?
Right.
Are they looking at the right thing?
Right.
Because there's some structure in here. There's some structure.
Yeah, like one thing is maybe like I think maybe we have some decent metrics. SAE bench is good. Like Matryoshka SAEs do seem to help on some of the metrics on SAE bench.
I see this.
That seems like maybe we have some hill to climb, but it's not a very clean hill.
Thank you, Josh. I really
Thank you.
appreciate it.
Yeah.
What an interesting.
Thanks.